our model was the AMD EPIC 7551P, which is AMD Zen processor with 32 cores. And the basic building block that was interesting for us was the core complex, which is consists of 4 cores with a shared free cache. 2 of those core complexes can then be connected to form a NUMA node via the scalable data fabric. And those NUMA nodes have a dedicated I/O and memory channels, hence the name NUMA node. It's a non-uniform memory access architecture. On the next higher level of the design, we have a package which in processors with more than one NUMA node, like our 32 core design, consists of up to 4 NUMA nodes being connected via the Infinity Fabric interconnect. What the most important thing is to take away here is that the processor consists of four NUMA nodes, which themselves consist of 8 cores. The next feature I want to introduce is dynamic voltage and frequency scaling. It's widely known that processors are limited in what they can consume power by their terminal design power. And what modern processors do to better use these thermal design power is to adjust voltage and frequency dynamically. A common feature in the realm of DVFS are so-called turbo frequencies, which allow processor frequency to increase beyond the nominal frequency. How this works can be seen in the graphic below, where if the processor features are fully utilized, we are using every core and every instruction to its fullest, the power consumption of a processor should be roughly equivalent to the thermal design power. However, if the processor is underutilized, the thermal design power is often not completely used. And here we can use turbo frequencies to make use of the of what's left of the thermal design power. The turbo frequencies in the AMD Zen architecture are guided by 2 main limits. The first limit being the all-core boost frequency at 2.55 gigahertz, which is the limit for cores if 4 or more cores are active in that NUMA node. If less than 4 cores are active, the frequency limit is the max core boost frequency, MCBF in short, because we haven't got a day, which is in this case 3 gigahertz. How this works, it can be seen in this very simple example. This schematically shows one of our processors with 4 NUMA nodes. And as you can see, the first NUMA node on the upper left corner is all cores are active in that NUMA node, so the frequency limit is 2.55 gigahertz. While in the upper right and lower left NUMA node, 3 and 2 cores are active, which is obviously less than 4, which means that the frequency limit is 3 gigahertz here. If we would activate another core in the upper right NUMA node, this would push the number of active cores to 4, and thus the frequency limit drops from 3 gigahertz to 2.55 gigahertz. Also notice that the number of active cores changing in the upper right NUMA node doesn't affect the usage of the max core boost frequency in the lower left NUMA node. To be able to achieve such high frequencies requires us to change the processor voltage. And in AMD Zen, this works in AMD Zen, the individual core voltages are regulated down from a global mainboard supplied global core voltage VDD CPU. The process of managing frequency and voltage works as follows. Every NUMA node has its own system management unit, short SMU, which controls voltage and frequency for its associated cores. In designs with more than one NUMA node, like in our 32 core design, one SMU will assume the role of the master SMU and which controls the VDD CPU. How this works is shown in this example. This mechanism is, I describe this mechanism as it is described in one of the A&D Lens engineers paper, which is cited below. And let's assume the core I've drawn in here that has a voltage of 0.85 volts, wants to increase its voltage, but it cannot increase it anymore because the VDD CPU is not high enough at 0.89 volt. What happens now is that the SMU of that NUMA node poses a request to increase VDD CPU to the master SMU, which then forwards that request to the mainboard voltage regulators, which then increase the VDD CPU to, in this case, 1.11 volt. This is relayed back to the master SMU, which informs the node SMU, and that node SMU then increases the voltage of the core. So now that we have some basic out of the way, I will shortly show you how we tackled the first question. What we basically have done was that we stress the cores individually with a synthetic workload. In a way, we make so in the first step, the workload runs on core 0, then on core 0 and 1, then core 0 and 2, 0 through 3, 0 through 4, and so on. And while we are doing was this, we have recorded some parameters. This is the overall system power, which we already recorded in the initial observation, per core frequencies, the per core voltages, and the global core voltage VDD CPU. All the code we have used to measure, all the code we have used for measurement, the scripts we use to generate graphs, and the data we use to generate those graphs can be found in the Git repository listed below. So let's look at the parameters piece by piece. And the first one we have looked at is overall system power. And what I shortly want to mention here is that one can clearly see the light violet error corridor. Error corridors are present in all graphics, but the error corridor can be very, very small, so it's not noticeable in a lot of them. And to shortly go over power, what we can see here is that we still had a drop at 28 cores, which means that our modified measurement setup still has this anomaly. So after we've looked at power, let's look at frequency. I want to introduce frequency step by step so that I can explain what happens, why the frequency changes in the way it changes over the run of our test. So what you can see here is the state at 3 active cores. As you can see, the frequency limit for those 3 active cores is 3 gigahertz because the criterion for maximal boost frequency is given. And what you can clearly see on the left-hand side is that the frequency is well beyond the lower limit of the all-core boost frequency of 2.55 gigahertz. It's around 2.85 and 2.75 gigahertz. So what happens in the next step? The now 4 cores are active, which means that the frequency limit is now just the all-core boost frequency of 2.55 gigahertz, and that is clearly shown in our measured frequencies as well, because the core frequencies drop below the 2.55 gigahertz line. And this also happens when cores in the next NUMA node become active. First, they exceed 2.55 gigahertz, and once 4 cores in the NUMA node are active, the frequency drops below the 2.55 gigahertz line. And looking into a larger picture, this is what basically happens for the complete run. Whenever cores in the new NUMA node become active, they can first make use of the max core boost frequency. But once 4 cores are active in that NUMA node, the frequency of those drop down below the 2.55 gigahertz line. What I quickly want to mention here, because it is a very interesting observation, is that the mean frequency of the active cores actually rises a little when the anomaly happens at 28 active cores, and while at the same time we have far less spread, and this is the first time that while these processors can all the time use the frequency up to the 2.55 gigahertz limit, this is the only point where they actually start using a frequency that high. So let's take the last parameter into consideration too, and that is voltage. I have charted per core voltage here, and the per core voltage behaves as we would expect it to behave. As you can see, when the frequency of a core is high, the voltage of its core is high, and when the voltage of that, when the frequency of that core drops, the voltage also drops. So this is also what one would expect. This is also behavior one would expect. So let's bring in the last parameter, and that is the global core voltage from which the individual core voltages are regulated down from. And here is where the interesting part happens, because what one can clearly see here is that the VDD CPU stays high even when all the core voltages drop down. To show what makes this so curious, let's look at this case. This is when 8 cores are active. The frequency limit is 2.55 gigahertz. None of the cores can make use of a voltage that high, and still the VDD CPU is that high. But practically the same is happening at 28 cores. I mean, here, none of these cores can use the high frequency here either. So what's the difference between the first one and the second one? Why is the VDD CPU low here, but not in the previous example? To show what we think is the cause for that, I have highlighted the NUMA nodes in this graphic in light green or light red. Light green means that because of this NUMA node have a frequency limit of 2.55 gigahertz. And light red means that the cores of that NUMA node have a frequency limit of 3 gigahertz. And you might say, okay, but none of these cores are active right now. How can they have frequency limit? What this shows is also, if we think about the theoretical frequency limit, if one of those cores would become active it would have a frequency limit of 3 gigahertz because it would be the first core that becomes active. And what we can see here is that for every state where the VDD CPU stays high, there's either a place where the frequency limit, either core where the frequency limit is actually 3 gigahertz, or a place where the frequency limit could be 3 gigahertz when the core activates. This continues when we continue through the experiment here at 90 cores and then at 24 cores. There's still a place where either it is used or it could be used. And what is now curious about 28 cores, the first one where the VDD CPU actually drops down is that this is the first configuration where the max core boost frequency limit of 3 gigahertz, when there is no frequency limit of 3 gigahertz anywhere, and there could not be a frequency limit of 3 gigahertz anywhere. So this is what we think is the cause of this. When we additionally look at when we compare configurations where on the left-hand side, the active cores are arranged in a way where none of those have a frequency limit of 3 gigahertz, and on the right-hand side, it has the same amount of active cores, but they are arranged in a way that the cores in that NUMA node could have a frequency limit of 3 gigahertz. We have seen that the power consumption of this with no frequency limit of 3 gigahertz theoretically or practically has a lower power consumption than this where it is theoretically possible. This has been also observed here where we have a similar setup. So the cause of this seems to VDD CPU, because what we found out VDD CPU does is that it stays high as long as the frequency limit of 3 gigahertz is possible and is possible somewhere. Not if this actually is used, if there is actually a frequency limit somewhere that is 3 gigahertz, or even better, if there is actually frequencies higher than 2.55 gigahertz allowed anywhere. No, the VDD CPU stays high as long as there is at least theoretically a 3 gigahertz frequency limit possible somewhere. So now what we have looked into energy efficiency we looked in the cause and can now look at the energy efficiency increase. The basic question here is, what is the impact on compute performance? Because having a lower power consumption is all fine and dandy, but if it's in the end just a trade-off, the higher power consumption configuration performs far better. It isn't that great, and for that we've looked at a set of different benchmarks which are bound by different parts of the processor design, which is the embarrassingly parallel benchmark, which is bound by raw compute performance, the multi-grid benchmark, which is bound by the performance of the cross-core communication architecture, the pointer chasing benchmark, which is bound by the latency of the level 3 caches, and the stream benchmark, which is bound by memory bandwidth. The setup for this part looks like this. In both cases, the benchmark is running on the cores 1 through 27, and as you can see in the baseline, there are only 3 cores active in that NUMA node, meaning that those 3 cores have a frequency limit of 3 gigahertz and 3 gigahertz. And to now get a configuration where no max core boost frequency is possible anymore, there are no limits of 3 gigahertz, just limits of 2.55 gigahertz anymore. We've just put an additional core into a simple busy loop. So now 4 cores are active, and the frequency limit drops to 2.55 gigahertz. So with that setup in mind, the results are as follows. What we've determined is that not only does the runtime of the benchmark it more so than the runtime of the benchmark being the same, the runtime even decreases slightly. This is due to what we have seen as I've discussed, the voltages, which is that after the anomaly happened, after the 28th core becomes active, the mean core frequency increases slightly, which for benchmarks that are bound by compute performance and the level 3 cache latency, which also runs of the core frequency, will lead to a slight increase in performance and was a slight decrease in runtime. Overall, if we multiply power and runtime reductions, we have observed energy savings of up to 9%. And concerning the benchmarks that are not in the realm of cores, the cross-core communication multigrid benchmark and the memory bandwidth stream benchmark, one can see that they are largely unaffected by the anomaly, which in my mind further indicates that the VDD CPU is to blame, as the cross-core communication, the Infinity Fabric network on chip, and the memory bandwidth and the memory run of a separate VDD I/O voltage, which is independent of VDD CPU. So if VDD CPU does strange things, as we have found out in our paper, then VDD I/O should be generally not affected by this. So to conclude the work, what we have found out about the anomaly is that the processor power management keeps the VDD CPU, the global core voltage from which all other core voltages are regulated down from, high, as long as the max core boost frequency could be theoretically used anywhere. It's not important if it's actually used anywhere, or if if it's actually used anywhere, just that there is a core that if it could become active, it could have a frequency limit of 3 gigahertz and need this high VDD CPU. The VDD CPU stays high, even when none of the cores actually need the VDD CPU to be that high. This, as we have seen in the second part, leads to less efficiency in configurations where less than 3 cores are active in one of the NUMA nodes. So which is the criteria for the use of the max core boost frequency. And as we have seen, because this is bound to VDD CPU, the reduction in power consumption is most noticeable in compute-bound workloads. And as a last point, when we looked at the successor architecture Zen 2, we couldn't yet reproduce any similar behavior. So that concludes my talk. I will thank you for listening to me, and I would accept some questions if there are questions.
So thank you very much. This was an interesting presentation. Any question from the audience? Okay, I have a very quick question. Did you get any official information from AMD about the issue and the root cause that you have identified?
We haven't contacted AMD in any way yet.
Okay. Another quick question. In your paper, you mentioned that you're not using REPL power readouts. Because basically they are based on a model on that system. Could you elaborate a bit more about why you think that REPL power readouts are based on a model? Because I was just curious about this.
Why? Sorry, was a bit quiet. So your question is why we didn't use RAPL
Exactly.
here. The problem with RAPL was twofold. It first of RAPL on AMD Zen is still completely untested, as there haven't yet been any studies to what the extent of accuracy is in what the extent of accuracy is for AMD RAPL. And secondly, compared to the overall system power, which we measured with a high accuracy power meter, it really didn't lead to new. We didn't learn anything from it. If I remember correctly, RAPL basically behaves. Per core RAPL basically behaves like the per core voltages in how the power consumption behaves.
Okay, thank you. Any other questions? Okay, so let's thank Christian von Elm again for his presentation. This paper concludes the session, and I give back to Romulo for the final remarks on this first PECS workshop.
Okay, thank you, Alessandro. Thank you all for participating to PECS. This is all for today, for the first edition of PECS. So I hope that you enjoyed the talks, that you find this interesting, and I'm looking forward to help to see you, all of you, for the future editions of PECS. So again, I wish you a nice day. I hope that you will enjoy the other workshop of ICT. So thank you very much for all of you, and hope to see you next year.
Thank you very much.
You. Bye-bye.
Bye to everybody.